Thanks for coming, y'all. I'm the mission design lead for Gateway at Johnson Space Center. So I want to talk to you a little bit today about how we use FreeFlyer on the Gateway mission design team. This presentation is taken from a conference paper I wrote with my colleagues Kathleen Howell and Fuad Khoury last February. So I'll go through it again for y'all. So the Gateway is our next human outpost in space. It'll be a proving ground for deep space technologies and a staging location for missions to the lunar surface and beyond Earth orbit. Our baseline orbit is a near rectilinear halo orbit near the moon. This is one of the halo orbits near the L2 libration point. Now, for power and thermal reasons, the Gateway wants to avoid eclipses that are longer than 90 minutes. So if you're clever, you can select and align a near rectilinear halo orbit so that it naturally avoids eclipses that are long due to the Earth's shadow. So once we've designed a baseline that avoids these eclipses, we need a strategy that keeps us in an eclipse-free phase near this baseline. So my goal today is to discuss eclipse behavior in the baseline NRHO, and then also discuss an orbit maintenance strategy that helps us achieve these goals in the presence of operational errors. So at Johnson, the mission design team for Gateway uses FreeFlyer to design our orbit maintenance algorithms, and then once we have those algorithms designed, to also compute the costs for the Gateway lifetime in attitude control costs and orbit maintenance costs. We do an orbit determination analysis for the Gateway. We also do trajectory design. Particularly, we've been looking at a departing flow from the NRHO, and then just for transfers in between the NRHO and other places. I also use FreeFlyer quite a bit to make movies and visualizations, which are a lot of fun. All right, so in this talk, I'm going to show some basically the results of some analysis that we've done regarding the phase control and eclipse avoidance topic that we've used FreeFlyer for. So first, let's take just a minute and talk about what an NRHO is. Okay, so this is what an NRHO isn't. This is a low lunar orbit near the moon, similar to what Apollo flew in. It goes around the moon every hour and a half or so, and it's in a circular orbit about 100 kilometers from the surface. Our NRHO is much, much bigger than this. So the NRHO gets 70,000 kilometers from the lunar surface at its farthest point, and it takes almost a week to make one revolution around the moon. So because its orbit is so big and gets so far from the moon, the gravitational effects of the Earth are significant. You can see the Earth is pulling the NRHO away from an elliptical orbit that it would be in if there were no Earth. So the extra gravitational effects offer both challenges and opportunities for mission design to help the Gateway orbit achieve competing objectives. And some of these are, letting our visiting vehicles get to and from the NRHO within their Delta V budget. It lets us stay in the NRHO for the Gateway lifetime without expending too much of our own prop. It facilitates communications with the Earth and the moon. We need to be able to get our astronauts to the lunar surface from the Gateway. We want to demonstrate cislunar transfers, so going from the NRHO to other orbits and back. And then, of course, what we're talking about today, we need to avoid long eclipses for power and thermal reasons. So our Gateway NRHO, even though it looks a little different than some of the more familiar orbits we may be used to, it does exhibit predictable behavior that lets us achieve these objectives. Okay, so what is an NRHO here? So what you see here in this picture is the L2 southern family of halo orbits. So these are, every one of these lines is a separate periodic orbit in the L2 halo family. So our near rectilinear halos orbits, which are shown here in black, is a subset of the halo family. The subset is defined according to its stability properties. And this blue NRHO halo orbit here is the one that's been selected as the current baseline for the Gateway. So this particular NRHO is at a 9:2 resonance with the lunar synodic period, which means that the spacecraft makes 9 revs around the moon for every 2 synodic periods of the moon around the Earth. So we have a repeating sun, Earth, moon geometry that we can take advantage of. Now, this orbit is nearly stable in a linear analysis, but it does require orbit maintenance to stay in it long term. We modeled our original orbit maintenance algorithm after successful halo orbiters. For example, so it's taken from a similar algorithm used for the WIND spacecraft and the Artemis Themis mission. Now, both Artemis and Wind, and Artemis, I'm talking about the Artemis Themis, the end-of-life mission for the Themis spacecraft, not the Artemis program going to the moon. So the Artemis and Wind halo orbiters perform station keeping without using any reference trajectory at all. It's actually simple to maintain a halo orbit without targeting a reference. And we know that the optimal maneuver directions align with a stable mode associated with that halo. So that the Artemis team discovered this when they were flying the Artemis Themis mission. Because our optimal direction is known, it's not necessary to re-optimize the maneuver every time you design one. But what we find is that for NRHOs, employing a baseline trajectory to use as a catalog of targets is useful for 3 reasons. It reduces cost and computation time, it facilitates planning for visiting vehicles, and it simplifies our eclipse avoidance processes. So our baseline gateway NRHO, this is what you see here is a 15-year propagation in a high fidelity force model. It exhibits a 9:2 resonance, as I mentioned, which means that the Sun, Earth, Moon spacecraft geometry aligns every 9 revs. So we have a repeating behavior. This allows us to avoid long eclipses. And we also use this reference as a catalog of targets for orbit maintenance. We find that strict targeting to this reference, like matching it precisely, all 6 elements, is quite expensive and it's really not necessary. So instead, we target components of the baseline, like a catalog. We use it as a catalog. And we target, for example, the X component of rotating velocity and then parallel passage time. And it allows us to remain near the baseline for low cost. Now, one of the reasons, as I mentioned, we want to remain near this baseline is in order to avoid long eclipses. So first, let me talk about eclipses that actually aren't a problem. And these are eclipses from the Lunar Shadow. So what you see here is the gateway NRHO in a sun-moon rotating frame. So FreeFlyer's nice this way because it allows you to set up various different rotating frames without having to do all of the rotation matrices yourself, which if you're me, that's really nice. So this is, I'm plotting the NRHO in a sun-moon rotating frame. And that means that the sun and the moon are holding still in this frame. So you know what direction the shadow is going to go, right? The light comes from the sun, it hits the moon, and the shadow's behind it. Because we're in a resonant orbit, we have a repeating pattern even in this sun-moon rotating frame, right? So you can see this pattern as we spin around the orbit in this view here. Now, it's quasi-periodic orbit. Since we're in an ephemeris model, it's not perfectly periodic orbit. So after 6 months, you do start seeing eclipses from the moon's shadow. And you can see that, I think this is after about a year or 2 has passed here. You can see that the pattern of eclipses has filled in, right? And you've got this, these white areas represent where the shadow hits on the spacecraft trajectory. So these lunar shadows, the shadows from the eclipses from the moon's shadow, it follows a periodic behavior over 15 years. So what you see here is a plot of eclipse durations in minutes, and along the horizontal axis is the epoch. So this spans 15 years, and you can see an annual period in the eclipses due to the lunar shadow. So we have no eclipses at all for the first 6 months, and then we enter into this this repeating pattern. But the maximum duration of these eclipses is less than 80 minutes, and so they don't surpass the 90-minute goal for us to avoid. So we don't have any plans to do any maneuvers or special things to avoid these eclipses from the Earth's shadow. They're just not long enough for us to be too concerned about. Anyway, and I'll give another shout out to FreeFlyer here. FreeFlyer will compute these eclipse durations for you, and so you don't have to write special scripts to do it. So that made this a pretty quick analysis for me. Now, okay, so these lunar eclipses are not too problematic, but Earth eclipses, on the other hand, can be really long. We haven't done a thorough analysis to find out exactly how long they can be, but we've seen them up to 5 hours, which is definitely over 90 minutes. So we want to avoid these, and that is why this trajectory was designed the way it was. And shout out to Dave Lee at JSC, who came up with this brilliant trajectory. So what you see is a gateway NRHO in the Sun-Earth rotating view on the left. So here the Sun and the Earth are fixed in the frame. And on the right is the Earth-Moon rotating frame. So as I've mentioned, the gateway goes around the moon 9 times during every 2 lunar orbits. So we get this repeating pattern of geometry. I applied the trajectory in white when it lies above the ecliptic plane and red when it's below the ecliptic plane. And I did this just using script, FreeFlyer script, to change the color when I want it to change. So what we know is that the sun shines on the Earth and casts a shadow behind the Earth. We risk eclipses when we cross the ecliptic plane. So during the red-white changes here, this is where we're crossing the ecliptic plane. So if this ecliptic plane crossing were to happen in this shadow, that's when we see a long eclipse from the Earth's shadow. But we've aligned the NRHO so that it always has a trough here, right? So you don't see a parallel passage or an ecliptic plane passage crossing when we are behind the Earth and in the shadow. So Dave phased the gateway within the NRHO to avoid the ecliptic plane crossing, so then they never occur behind the Earth. So you can see this in another view here. So on the right here, we have 15 years of the baseline trajectory. And what we're looking at is we're looking down on the sun-Earth rotating frame. So the sun's over here on the x-axis. We can say it's here, in fact. And it's shining its light on the Earth, and the shadow is cast behind it. So in this XY view, we're looking down on it right now. The red are the parallel passages during the 15-year gateway baseline trajectory, and the blue is the ecliptic plane crossings. And you can see that they don't happen where the shadow hits. This is a plot of all 15 years of the trajectory, and I've turned the plot white when we are in eclipse. So in this 15-year baseline, there are two tiny partial eclipses due to the Earth's shadow. But in operations, these actually go away. Oh, I thought I had another plot here. All right. In operations, the plus in the paper. These all be, once tiny adjustments as you fly this trajectory over 15 years, I mean, these guys go away by the time you actually get to them. So they're not too much of a concern. Okay, so here's again our baseline trajectory in the sun-Earth rotating view, and in our more familiar, perhaps Earth-Moon rotating view, where you can tell that it really is a quasi-periodic orbit. Now, this orbit is not quite stable. It's very close to stable, but it's not quite stable. So without orbit maintenance, the spacecraft will depart the lunar vicinity in 5 to 14 revolutions, where each revolution is 6.5 days. So you have a few months before you'll escape in any case. But we do need to stay near the baseline orbit to make sure that we remain in the NRHO and avoid long eclipses. And we've modeled our orbit maintenance strategies based on Artemis and Wind orbit maintenance algorithms. So we have to consider operational errors when we're doing analysis on this spacecraft. So for what I'm showing today, I'm only looking at a simple case of an uncrewed gateway. Now, in actuality, we expect to have objects coming and going, docking and undocking, crew coming to visit. But right now, we're just going to look at 15 years of a quiet spacecraft in an NRHO. So we have a set of baseline errors that we consider. We look at solar pressure, momentum wheel desaturations, navigation, maneuver execution errors. And we've defined like a baseline set of errors, and then I wanted to bound the costs that we're seeing. And so we have a set of errors where everything is tiny, a set of errors where everything is large. In the paper, I vary these one at a time, but I don't think I did that in this presentation. But mostly we'll be focusing on these baseline errors. And so once these errors are applied, we have, like I said, 5 to 14 revolutions before we escape. And so we don't want to escape. And so we would perform orbit maintenance. We can start with this simple algorithm that, again, we based off of the Artemis and Wind type of algorithms, where here we are in our NRHO, the spacecraft's going around, and we allow a maneuver close to apolune, not necessarily at apolune, near apolune every rev. And what we do is we target components of the baseline trajectory at parallel 6.5 revolutions downstream, or some amount of time downstream. So one thing we can target is the x component of rotating velocity. If we target close, like half a rev ahead, that's going to be a higher cost, because in orbits, it's always cheaper to target further ahead. If we target too far ahead, then convergence gets challenging in our targeter. So what we settled on is if we target 6.5 revolutions ahead, that's a pretty good balance between cost and reliability. And then we only execute the maneuver if it is above a particular threshold. let's see, I think I've said everything that's here. So if a convergence fails, we can reduce the targeting horizon. And if the minimum maneuver threshold, or if the targeted value is greater than a minimum maneuver threshold, then we execute the maneuver. What actual threshold you choose might vary based on what kind of errors are acting on your spacecraft. Now, this is kind of nice, actually. In FreeFlyer, we use the differential corrector object in FreeFlyer to do this. And that let us do things like integrate in the inertial frame and yet target the rotating x velocity in the Earth Moon frame. And I didn't have to do the math myself to do that. I can just ask FreeFlyer to, with its differential corrector object to achieve, vary the maneuver components in order to achieve a particular value of rotating x velocity, even though we're integrating in the inertial frame. So that was super nice. Okay, so this simple algorithm, we are targeting just Vx equals Vx ref. So the value of the rotating x velocity along the reference trajectory at its paraloon, 6.5 revolutions downstream from our maneuver. So it's just one component. We're just targeting one thing. And what you see here is a single Monte Carlo trial for 3 years propagation. So each year is about 56 revs, since each rev is about 6.5 days. So you can see year 1, year 2, year 3. Our orbit maintenance burns, I think the minimum maneuver threshold here was 3 centimeters per second. So you can see that they range from in this single Monte Carlo trial, from 3 centimeters to 8 centimeters per second a piece. And we skipped more than half of them. You can see all these 0 burns here. That's because we skipped those maneuvers. They were below our threshold and we didn't perform them. You can see that over these 3 years, this particular trial cost about 2.5 meters per second. And the paraloon passage time, though, has drifted by over 10 hours. So that's kind of a lot if you want to avoid eclipses. If we look at 100 trials, of the same 3-year propagation, we can see that our burns remain, again, between about 3 and 10 centimeters per second. And the costs are just under 1 meter per second annually. This is 3 years. But our paraloon passage time drift is getting rather large. So we're over, for some of these worst cases, we're over 50 hours off of our reference paraloon passage time. And so at this point, you're not in the same phase as your reference. And so there's no guarantee that you're going to avoid your long eclipses from the Earth's shadow. And so this is 3 years. If we look at the same analysis, so 100 Monte Carlo trials over 15 years, well, now we see that we really can't guarantee that we're going to stay out of eclipses. Our costs do stay relatively low, though as you get farther and farther away from the baseline, targeting back to the baseline can be more expensive. So this paraloon passage time drift can complicate things. It can complicate planning for visiting vehicles who want to know where they're going to go, where they're going to find you when they launch. And it also means you can drift into eclipse. For example, here's a single one of those 100 Monte Carlo trials that I've propagated. And you can see right here, these white pieces are the ones. So basically I asked FreeFlyer, plot the spacecraft in blue if it's not an eclipse and plot it in white if it is an eclipse. And you can see right here where the eclipses happen. And you can also see that our nice pattern that avoided the x-axis here is gone. So we do have ecliptic plane crossings and paraloon passages in this region here. So we do, without maintaining the phase, we do drift in this particular trial into eclipse. And you can see them here. We have, I think I counted these, there's like 11 or 15 or something eclipses that were over the 90-minute limit. So we need to have a strategy to avoid eclipses. You could do this in a few ways. You could, compute upcoming eclipses and do maneuvers to avoid them. But a cheaper method is just to maintain your phase within the baseline trajectory. Okay, so before we do that, this is the simple algorithm without phase control, where we target only the single component of the baseline trajectory, the x component of rotating velocity. So I'll go through this first and then talk about how we augment it in order to achieve phase control. So without phase control, we schedule an orbit maintenance burn at Apolloon, and we target Vx at paraloon 6.5 rows downstream within a tolerance, right? And if our convergence fails, we reduce the targeting horizon until the convergence is achieved, and we execute the maneuver if it is below a threshold. Otherwise, we skip the maneuver. And with this, as I just showed you, we can maintain the orbit indefinitely, but the cost can grow over time and the phase is not maintained. So instead, we augment the orbit maintenance algorithm with a phase control strategy. So what we do is we simply add one more component to the targeting at Paralune. It's pretty simple. We step the spacecraft to a true anomaly of 200. It's not effective to target Paralune passage time if you do it right at 180. So you can do it at, for example, a true anomaly of 160 or a true anomaly of 200. You perform the orbit maintenance and you target, again, you just target VX. And this provides an initial guess for your targeter. I'm not using an optimizer because we know what the optimal direction should be. And we achieve such low cost just using a targeter that it's not worth the computational time to re-optimize every time. So we're just using a targeter. But to do that effectively, we start with an initial guess. And our initial guess is we just target VX equals the reference value. But we don't execute this maneuver. We use the computed delta V as an initial guess to target both the same thing we just targeted, VX equals VX along the reference trajectory at its Paralune, and the Paralune passage time of our propagated trajectory equal to the Paralune passage time of our reference trajectory within a tolerance. Where this target is a weighted value of Paralune passage time, it's not super effective to target it precisely, but in the paper you'll find the equation for the weighted Paralune passage time. Anyway, so if the convergence fails, we reduce the targeting horizon until it's achieved. And then if the delta V is over a minimum threshold, whatever we choose that to be, we execute the maneuver, otherwise we skip it. So by doing this, just targeting, allowing one maneuver per rev, targeting two things off of the reference orbit, we can maintain the orbit and the phase indefinitely. The costs remain low over time, and we maintain the phase. So let's look at some of that. Okay, so this is a reminder. This was the orbit maintenance, a single Monte Carlo trial of 3 years without phase control, all right? And we remember that our Paralune passage time drifted by over 10 hours in this example. So now we'll add phase control, and you can see another single Monte Carlo trial. You can see that the delta V's for each maneuver, again, they are, sort of between 3 centimeters per second and 8 or 10 centimeters per second. Again, we skip over half of the burns, so we don't have to perform them. But our Paralune passage time drift is under an hour the whole time. So it remains less than an hour over the 3 years. So we can look at 100 Monte Carlo trials of this 3-year propagation, and we see similar behavior. The orbit maintenance burn themselves remain bounded. Our total cost for this 3-year propagation, again, is about 1 meter per second annually. And our Paralune passage time drift remains bounded. If we look at the same thing for 15 years, this is sort of the money shot here, we do see that it works nicely for the full 15-year baseline orbit. We'll start here on the bottom right. This is the Paralune passage time difference between the baseline and the propagated trajectory. And this is 800 and something revolutions, so it's 56 revolutions per year. And we've got 15 years going on here. So for the whole 15 years, all 100 trials remain less than an hour away from our baseline. And you can see the cumulative delta V stays at about, we've got one little outlier going on here, but it stays generally about 1 meter per second annually. And then the position drift, so if you measure this, our propagated gateway position at Paralune and compare that to the reference trajectory at its Paralune, the delta position remains under 100 kilometers or so. So that's bounded for all 15 years. So it works relatively nicely. So it's a simple algorithm. It doesn't cost much because this orbit's nearly stable, and it keeps us both in time and in phase long term. Now, I talked about the large and the small bounding errors. So if all of our, this is like best case scenario and worst case scenario. So if we have everything behaves absolutely beautifully, in tiny errors, we might cut our delta V in half. This is about 0.5 meter per second per year. If the whole 15 years acts like the year 2020 and everything that goes wrong can go wrong, we see it costs more, about 4 meters per second annually, up to 60 meters per second for the 15 years. So it's still quite small. For comparison, if you're trying to do station keeping in a 100-kilometer circular polar low lunar orbit, you're looking at 60 to 100 meters per second per year. So this is definitely a lot cheaper than maintaining the orbit in a low lunar orbit where you're fighting the gravitational parameters of the moon. So in all these cases, we saw 100% convergence. The worst case was about an order of magnitude more expensive than the best case, but it's still pretty low. And these simulations are for uncrewed operations only. So really, you can imagine if you're Capstone, the small CubeSat that's going to go fly around in an NRHO. I think it should launch next year, which is super exciting. So if you're Capstone, you're going to hang out there for 15 years. These are the kind of errors that you might expect to see. But we simulate this simple situation in order to design the algorithm, and then we do also, of course, with FreeFlyer, 15-year simulations of orbit maintenance costs and attitude control costs, assuming all the dockings and the perturbations that you expect from crewed missions to Gateway as well. I also tried to break this because we had a pretty cool algorithm design to get back to the NRHO if we accidentally left. And so I tried adding large perturbations annually to this, and I just couldn't get the algorithm to break, which I guess is a good sign. So in other words, even with large perturbations that could simulate a crewed docking, for example, the algorithm did remain robust. All right, so let's talk a little bit about maneuver placement. Here's your NRHO, right? I've written down some true anomalies here. So even though this is not a conic section here, we can still use true anomaly as a measure of where you are within the orbit. It is still, I find it to be quite useful. So what we find is if you're targeting only VX, if you don't care about your phase within the NRHO and you're only targeting VX, putting your maneuver in between 170 180 tended to be the best place to do it. And if you get earlier in the orbit, then true anomaly about 165, or later in the orbit, then true anomaly about 195, it tended to fail in some trials over the long term. And that's because as you get closer to paraloon, your orbit gets very sensitive, and errors in maneuver execution and navigation can cause your trajectory to diverge. So this is more of a preliminary rule of thumb, and the bounds will depend on what errors you're assuming on your spacecraft. When you add the second target, the parallel passage time target, we found that performing the burn at a true anomaly of 180, while it's effective over short term, it wasn't effective over 15 years of full long-term propagation and simulation. But if you move the burn to either a true anomaly of 200 or a true anomaly of 160, it worked quite beautifully. For operational reasons, we're assuming true anomaly here of 200 because as if you back up from the burn, you start to get close to parallel in this case, and so we're assuming that we do a burn perhaps at a true anomaly of 200 when we want to target both VX and TP. All right. Now, burn directions is also an interesting study. So we remember from the Artemis and Wind orbit maintenance that though the teams at Goddard who performed and still perform the orbit maintenance for those spacecraft have found that the optimal direction for an orbit maintenance burn is in a stable mode direction associated with the halo orbit. So you don't know, there's statistical errors there. It's not like a drag at the Earth. So you don't know if it's going to be a positive direction or a negative direction, but you know it's going to be in the stable mode direction. And that's also what we find in Gateway. So this is a simulation of 100 Monte Carlo trials for, I can't remember if it was 3 years or 1 year or 15 years in this plot. But on the left, you see the burn location and direction at Apollon. And on the right, you see the unit vector. So on the right, I've taken all of these burn vectors and plopped them at 0, 0 and propagated just the vector. So these are aligned with the stable mode associated with the halo orbit. We don't know, again, in advance if you're going to have the positive direction or the negative direction. But they're largely in the Earth-Moon plane with a small out-of-plane component. And we do have direction variations that follow a monthly pattern. So this is pretty cool. Now, when you add your parallel passage time targeting, you have a different pattern here. So you have a more complex pattern, but they still follow a pattern. They all line in a plane like bicycle spokes or like a chimney sweep brush here. You can see We're still investigating as to why exactly those directions are selected. We're not 100% sure, but these are the directions that we see long-term when we're targeting both VX and parallel passage time. So this is where each burn direction is placed at its location in the Earth-Moon rotating coordinates. And then the unit vectors are here on the right. All right, so in summary, the analysis that I've shown here, it's been talking about shadowing and orbit maintenance. So we know that we get a periodic pattern in lunar shadows from the moon's, so eclipses from the moon's shadow. But all the lunar eclipses we expect to see are less than 80 minutes in duration, which aren't terribly concerning. The Earth eclipses can last much longer, and we'd like to avoid those. So what we've done is designed a baseline NRHO that is resonant in the lunar synodic frame. So we have a repeating Sun, Earth, Moon spacecraft geometry that allows us to avoid the eclipses from the Earth's shadow. We've also achieved long-term orbit maintenance within this trajectory for a spacecraft flying in it. If we target only VX, the way Wind and Artemis did it, we maintain the NRHO without any trouble, but we do have a drift in phase, and we may drift into eclipses. So if we add parallel passage time as a target, then we can maintain both the NRHO and the phase for low cost. This algorithm is robust and it doesn't cost too much. We do see patterns in the burn directions, which is nice, but we can't predict the positive or negative sign along the vector in advance because these are statistical errors acting on the spacecraft and they don't occur, they're not deterministic. This current presentation focuses on uncrewed quiet operations. We've also, in our analysis, shown that this algorithm is also robust for 15-year gateway simulations that incorporate annual crewed missions. So this is the paper that we wrote back in February about phase control and eclipse avoidance. We presented this at the AAS GNC conference in Breckenridge back in February, if you want to look it up. And I'm happy to take any questions if you have any.
So the first one is, how does SRP solar radiation pressure affect gateway orbit?
Okay, so we do model it. So this is interesting. The solar pressure is not incorporated in this baseline trajectory that you see here. So this baseline, there's a white paper that describes it that was written by David Lee. You can find it on the NTRS NASA server. I think if you just go to NTRS and search for NRHO, the white paper shows up. And anyway, this baseline is out on the JPL-NAIF server. It does not include solar pressure because this trajectory was designed before the spacecraft was designed, and we didn't know, and it's just for whatever spacecraft, right? So let's see if I have this in my backups, actually. Do I? No, I don't. Okay, so the reason I don't is that the solar pressure does not affect us very much. And so it wasn't worth putting in the backup slides. The solar pressure has a small effect on our orbit maintenance costs. We model a flat plate models using FreeFlyer. And we also have a paper out there that showed the difference between using a flat plate model versus using vectors and 3D modeling, and it was very small differences. What is more important is the solar torques. So what we do is we use FreeFlyer to compute an equilibrium attitude, a solar pressure equilibrium attitude, so that the solar torques don't add attitude control costs to our spacecraft. So that's really the bigger effects. The solar pressure itself isn't bothering us much. The solar torques can be bigger, and so we design an attitude to minimize those torques.
Gotcha. Another question from our team. Selfish question. How do the new FreeFlyer 7.6 features like optimization, relative motion, plot enhancements, how do those help the gateway team and your work that you're doing?
Well, one thing that the optimization has done, we don't optimize the burn directions, as I mentioned, because we kind of know those already. However, we've used the optimizer to help us select the correct thruster. So if we want a burn in a particular direction, if we have several available thrusters on the spacecraft, we can use the FreeFlyer optimization to select the the thruster pairs or combinations that will give us the burn direction that we want. I also love the new plotting capabilities. And well, some of this came out in 7.5, but when I'm making movies, it lets me rewind and go forward, and it's just fantastic. Saves me a ton of time. I like that.
Great. Question from Conrad in the audience. Can you explain the 10 times difference in delta V for the two maintenance methods with and without phase control?
Sure. So I think what we're talking about is this guy, which was 15 meters per second for 15 years, right? Versus up here, over 15 years, it got all the way up to, well, maybe not 10 times, right? It was maybe 40. But basically what's happening here is that if you look at the best case scenarios here, they're the same cost, right? And that's what's happening is that your phase control has not shifted. I mean, your phase is maintained for these particular, it's 100 Monte Carlo trials, and these particular guys, your phase hasn't shifted, so you're still targeting a baseline orbit that is similar to what you're flying. And so what's going on up with these guys is that you're in a way different place in the NRHO, and so you're targeting essentially the wrong rev in the baseline, and so your cost goes up because your reference, the baseline is no longer a good prediction of what reality looks like. Now, what Conrad may have been asking was this guy here, the 10 times difference between the small errors and the large errors. If that's what you're asking, then basically what we did is said, okay, your small errors is everything is going as well as possible. You have tiny navigation errors. You have small maneuver execution errors. You don't have any desats at parallel. And your parallel delta V is, or your desaturation delta V is very small. Whereas your large error values, you've got 5 desats at parallel, and preparing the spacecraft at parallel is very sensitive there, so we don't like doing it. With a large delta V due to each desat, you've got desaturation errors of 10 centimeters per second apiece and large execution errors. And so basically, if you've got your baseline errors here, that gives us our 1 meter per second annually. If you have all the small errors, you get the low cost. If you have all the big errors, you get the large cost. So that's the difference. And really, what's really driving it is the nav errors. You can see kind of a linear behavior in annual delta V versus your nav errors. And also the desats. So if your desat perturbation grows, then your delta V grows. And if the number of desats grows, then your annual delta V grows as well.
Gotcha.
Hopefully with one of those answers, hopefully that explains it.
Thanks, Diane. We've got a number of questions that I'm going to kind of attempt to combine here about thrust modeling for the Gateway program. So can you start off maybe telling us a little bit about what kind of thrusters will Gateway have, how many thrusters, and then how are you modeling that? Are you modeling them impulsively with finite burns? And how would you expect, if you're using electric thrusters, how would you expect that to affect your results?
Okay, so we have 2 different types of propulsion on the Gateway, and we have solar electric propulsion that use xenon propellant, and we have RCS thrusters that use a biprop chemical thrust. We use both for orbit maintenance. We assume that we use the xenon during uncrewed operations, and we use for orbit maintenance because it's much more efficient and we use less prop per meter per second delta V, for example. If we need to do a burn more quickly, then we do a burn using the RCS prop. So what we do is when we're targeting, let me back up to a picture. When we're targeting the burn, we do actually the targeting using the impulsive maneuver modeling in FreeFlyer because it's simpler to execute. And then we convert that to a finite burn using just the rocket equation to get a maneuver duration, for example. But it's the impulsive burn is a good enough approximation that it works fine, even with a long solar electric burn. We were able to target using impulsive. We've tried it both ways, and it's just faster to target with impulsive, and it doesn't buy you much to target using the finite burn modeling. So we target with impulsive, use rocket equation to convert to finite, and then use that in our simulations.
Gotcha. You talked about faster and slower. How are you setting up things like a Monte Carlo run? Are you doing those in series or in parallel?
They're in series more or less at this point. We generally run our simulations on we might use 6 cores at a time, and so, but it's not it could be parallelized, but it's not the way we're running it right now.
Okay. Question from Rashid in the audience: how are the initial conditions for the NRHO orbit calculated to get that initial orbit?
Okay, so how did we get this guy, right? All right, so this particular, there are many ways to do it, and it depends on what it is that you want to do. So in general, what we do is we start from a circular restricted, perfectly periodic halo orbit like this guy up here, right? This is a circular restricted model right here. Each of these is perfectly periodic and in a circular restricted 3-body model. What we do is we take patch points off of this, and then we can use various methods to convert it into an ephemeris model. So Brian McCarthy coming up is going to talk about one of those methods. It's called a 2-level targeter that he's written in FreeFlyer. So he's going to talk about that. Dave did this. It was actually in order to avoid all the eclipses. I believe it was a rather time and engineer intensive process in order to really perfect this. I'm sure there's a way to automate it, but I know that there's a university who are working on different methods to put constraints into the process of converting from a circular restricted approximation to a high fidelity ephemeris. But for one of those methods, wait and listen to Brian, who's coming up in, I think, after Michael today.
Yep. You talked about time intensity and things like that. For this 15-year orbit that we're looking at, how long does that actually take to propagate in FreeFlyer?
Okay, so I mean, I made this picture just by stepping through the ephemeris in FreeFlyer. So you can propagate with a RK45, for example, or 8.9. I think this is an 8.9. But this is just stepping through the ephemeris. So I can feed, and we had a Spice kernel file that I read into FreeFlyer, and then I've converted that into a FreeFlyer ephemeris native form to make it easier to work with. And you can step through that ephemeris. I mean, it's very fast if you minimize your screen. If you want to watch it go, then it's a little slower. It just depends on what you're after. You can't just grab an initial state off this and propagate it with an RK89 for the whole 15 years because it is mathematically unstable. So even if your errors are 0 and you use the same script in the same setup to generate the orbit as you're going to use to propagate the orbit, it's still going to diverge over time due to buildup of numerical errors because it's a mathematically unstable orbit. So even best case, it's after 14 revs, 14 weeks, it's going to escape from the NRHO, which is why we do orbit maintenance. To do one Monte Carlo trial, now you're going to ask me how long. I think to do 100 for 15 years took a few hours to do the orbit maintenance burn for that. I think when I did some cases that were 500 trials for 15 years each, it would run overnight. Not terribly long.
Yeah, absolutely. That's awesome. Thanks for kind of explaining that process and the numerical uncertainty there. You brought up the capstone mission. Can you tell us a little bit about what that is and what is your team looking to learn from that mission as you move forward to Gateway?
Oh, sure. Okay, so the capstone is a CubeSat mission. It's going to launch next year. It's going to be flown by our colleagues at Advanced Space, and it's going to this NRHO, which is super exciting. And it'll be the first spacecraft to use this orbit maintenance algorithm, and it'll be the first spacecraft to fly NRHO. So I'm super excited to see all this in motion and in action. The Advanced Space folks we've got a few of them on our Gateway mission design team as well, and so we work real closely with them. So I think they'll be able to basically prove how behavior works in the NRHO, what challenges we may find, prove that the orbit maintenance works, that we are getting the perturbations we expect. Yeah, I think it's going to be really neat to see.
That's awesome. I'm just checking to see if we've had any more questions come in. See, Michael Volley is asking if you've tried parallelizing Monte Carlo so far, or have plans to.
Yeah, we're talking about it. We potentially, yeah. We have one particular person on our team who's really excited about the idea and is getting FreeFlyer set up on a server here. So we'll see potentially, yeah.